In this video, we will be solving Fun, which is a reverse challenge from Zh3r0 CTF 2020, and it was worth 499 points. So a quick overview for this challenge. It was a reverse challenge. The binary was x86-64 ELF, and essentially it implements a password checker. So the overall strategy here is to reverse engineer, first of all, the password transformation algorithm. In other words, figure out how the input gets transformed, and then reverse the actual transformation to get the correct initial password. So a quick overview of the binary, we have the transformation algorithm is a long sequence of operations. As you can see here, this is just a small snippet from the overall graph view. If you actually open it up, it's actually extremely long. You won't be able to see everything in complete detail. However, there is an order to the madness here, and essentially there is a periodicity in the instructions. So if we just briefly look around here, we can see just by spotting this instruction here that kind of pops out, the move SX EAX byte pointer RSI plus something, you can see that it occurs about every 9 instructions here. And so this is the periodicity in this sequence of instructions. So this suggests that the password is being operated on with a series of similar operations. So I didn't show this here, but at the end, the transformation result should be 0. And what I mean by that is, if you'll notice at each of these sections, we'll talk about this a little bit later, but in each of the periods, you have a D word being affected, and it's being changed at every one of the periods. And at the end, all of them should be 0. So actually, here is a view of the final checks. We can see that it takes all of these values at the various offsets, and then it checks them to see if they're 0. And if they are 0, then we continue. Otherwise, we take this branch with the jump if not 0 to invalid password. So our goal is to get every one of these values to be 0. So let's analyze one period of transformation in more detail. So here's just one taken in a random location. This is at offset 3A46 in the file if you want to follow along. And here I've included the disassembly view as well as the hex view of this period. So actually the hex view starts here. This is from the previous period, and it goes on till the end of the block here. So what essentially happens is we have move into EAX of RSI plus hex C. So this is an offset, and as we saw earlier, the offset changes with each period. And then we have a move ECX from double word pointer 6040 relative to CS, and a move into EDX of 6074. So let's see what happens. EAX is multiplied with ECX. So in other words, this value here is multiplied with this value here, okay? And then the result is added to this result here. Okay, and then this result, which is now an EAX, remember IMOL only changes the destination operand here. That result gets stored into 6074. So that was this guy here. So essentially what's happening is we're taking the input here, multiplying it by some constant at 6040, and then just incrementing 6074 by that amount. And then what we do, this 3 instructions here, we move whatever's in 6040 into EAX, then add 2 to that, and then store it back. So essentially this is just adding 2 to whatever is in that location. Okay, so what instructions are present here? We already kind of talked about this, but we have movement, several move instructions. We have move IP relative into these 3 registers, and each of these registers has a different associated reference. So ECX and EAX, as we saw on the previous page, always references 6040, which we saw here, and EDX references 6074, or the EDX register comes from 6074. We have a move RSI based index into EAX, and actually this contains user input. So this piece of code here is executed at the very beginning. We see what happens at first is this is in the entry, so RSI is set to argv, and moving the value at RSI plus 8 into RSI, remember this is 64-bit, so RSI plus 8 is actually argv1. This is the input that you supply in the command line. So in the remaining of this remaining part of this binary, RSI always references that argv1, and any offset is relative to that string that you input. We also have a sign multiply between EAX and ECX. This is the integer, the imul, and addition of EAX and EDX, and addition of the immediate value to EAX, and that is, of course, here. So the overall operation of this piece of assembly is to do this. Okay. Yeah. So some additional observations. If we look at some different periods, right, we see that pretty much everything is like this, with some up to some slight permutations in the order of the actual instructions. And in each period, we always have a load from 6040. So going back to this page, we can see that there is always a reference to 6040 here. And this is always used in the calculation. And in fact, it's always the one that's being multiplied by EAX. And the other address, so we see here, we have 6040, but we also have another value, 6064 in this case, or 6074 in this case. This references a transformation value that is checked at the very end to see if it's 0. Okay. So all the periods are pretty much like that. So all periods implement something like this, you know, up to this operation here, up to this constant here, up to this offset here, and up to this value, storage value here. Except for two kind of special cases. One of them is where we have something like this. So in this situation, we see that there is no move EAX from RSI, and in fact, the register order is all wrong, and we can see that here. The register order is all wrong. However, the overall instructions are the same. So we still have a multiplication of the 6040 value with the RSI value, and we add that on to the other value and store it back to that value. But this time we just don't have a subsequent load. But notice that our EAX here is not modified, so it retains its value, and it's kind of used down here. So in this case, it's essentially just the value isn't changed at all. The user input value isn't changed. We still read from offset hex C rather than changing that where we read from. The other situation is something like this, where we have a move from 6074 directly into EAX, and then we have a subtraction of an immediate value and then a storage back into that location. So this is a kind of a special case, but you can think about this as just kind of adding an immediate value to that memory location. So from here, where do we go? We know what the kind of binary kind of does, and have a general idea about how we want to engineer our input so that we can get the correct output. So here we reach a crossroads. There are two kind of main ways we can proceed. One of them is just doing each section, so going through the assembly by hand and parsing every set of instructions and basically writing the equivalent value like we did here and doing that for every one. Or we could write an interpreter that will kind of read through the binary of this critical section, and it will kind of parse through and give us the high-level operations about what's happening. So here I have a rudimentary graph of the time versus the amount of output that we provide. So for an automative approach, we start out, of course, writing the actual automation process, and this includes, of course, debugging. And this during this period of time, we have no output, okay? But after a certain point, after we get the automation working, so this is this vertical line here, the rate at which we produce output is extremely fast because the script, of course, is running very quickly, much quicker than we can do by hand. And of course, this figure is not to scale. This line here actually may be vertical or nearly vertical, right? Because the computer can read through the code and process it much faster than we could ever hope to by hand. But this red line represents basically doing each section manually. We can start right away, right? There's no loss of time here. We produce output immediately, but as we reach a certain point here, we start to get slower growth than the automated approach. So the general idea for this kind of challenge is you want to kind of estimate where on this output axis the challenge is. So for some very easy challenges that require very small amounts of workload, your output is quite low. So you'll be down here, and if we draw a horizontal line of constant output, we can see that the amount of time it takes to parse each section manually is actually far less than the amount of time it would take us to do it with automation, right? Because we don't have to spend all this time producing nothing. However, most challenges, most challenges of interest are going to be above this line, or above this horizontal line. So maybe somewhere here, and we can see that that the amount of time it would take us to use the automated approach is actually shorter than the amount of time it would take us to do it manually, and this gap just increases as time goes to infinity. Okay, and this makes sense because after we've written the script, basically there's no extra time that we have to wait to get results, right? And this the time spent writing the automation becomes very small compared to the break-even time, or sorry, to the time it takes us to do a certain amount of work by hand. And where the two intersect is kind of that nasty point, because you don't know what to do, whether you should write an interpreter or parse the section manually, but you're going to get similar results in either case, similar times. So I decided to implement the automation approach because if you saw, the actual procedure is quite long. So for this, I implemented a binary state pushdown. So why did I do that? Well, because if we look back at how this process works, we have a series of basically registers, a set of memory that retains value, right? So we need that kind of memory there. But by reading through the instructions, we can figure out what's going on. So for example, if we read a hex F, we're going to go to one of these instructions, either an imul or a move SX into EAX. If we get an AB, we'll go to this set of instructions, which could be any of move ECX, move EDX, or move EAX. Okay, and these are only two of the cases for the initial byte. There are actually several other first bytes that we could have. And this graph kind of shows how we progress through the bytes, how we basically accept the byte, and then what we do based on that. And of course, if we reach something that we don't expect, we drop down to error. When we reach one of these terminal nodes, we want to perform some special operations. So, for example, if we have a move SX, EAX, RSI plus some non-zero constant, then what we're going to do is read that constant, which is present as an immediate byte, and then store that into a memory location manip before we emit it out. And the time when we print, basically to print the high-level instruction, is when we have that move back into that memory location. And that's not pictured here, but essentially that's what it does. So when we run this automation, we get this output. So this is actually the complete output. I've just kind of cut it up because it's a very long sequence of instructions. And there are actually 274 total. So this is quite complicated. However, the system is linear, right? Because at each step, all we're doing is taking some constant value that we can predict and multiplying it by some of the variable. So the system is linear. So after we get this output of the automation, we're still not done, right? We still have to kind of arrange this into a linear system. So, but the procedure here is much easier than the previous step. All we have to do is read each line of the output and determine whether the instruction modifies a coefficient. In other words, it adds on a certain multiple of the input password, or if it's just a constant. right? And that's from those instructions. You can see kind of here's a instruction that modifies a constant, and most of them are modifying coefficients. Okay, and back in the code, this is where you would see a modification of the constant. And most of these are where you see modification of coefficients. Okay, and then you modify the linear system accordingly. So this is kind of the code that generates that matrix. And if we print the matrix out, this is what we get. So we can see that it's here shown is a 16 by 17 matrix, 17 because we have 16 variables and then one non-homogeneous term. But actually, I lied. We actually have one extra equation at the bottom that I didn't put in here. There are actually a total of 17 equations, but if you look at this equation, it's kind of defective, right? There's a 31 and a 15, and the output is 0. So this is probably not checked, and we can probably verify this by going back into the to the binary. And we can see that this value here is not really checked. So here we go. We're going to solve the system, and to do that, we can use NumPy linear algebra toolkit. But when we do that, we get something weird, and actually this is wrong. When we solve the system, we get something that's close, but it's not actually correct, which is kind of interesting. But we can actually use MATLAB, and we can get the correct answer. So here's the correct answer printed vertically. I actually did this because I just row reduced this system here. I just import directly into MATLAB. And when we transform these back into character values, we get our flag. Or actually, we get this part of the flag. This is 16 characters, but then we just enclose it in the flag format, and we are done. Okay, so that's pretty much it for this challenge. Some big takeaways from this are really this this strategy here, figuring out where you are on the output. Usually easier challenges, you know, it might be better just to go through the binary and parse everything manually. But once you reach a certain level of workload, it just becomes kind of impractical to parse through the whole thing. And in this case, I believe we were certainly up in this range because we had a total of 274 operations. This could take probably like up to an hour just to go through all of these. And also, it's prone to mistakes, right? So, yeah, that's pretty much it. And I hope you enjoyed, and I'll see you in the next video.